Xiao, do we have everyone entering already, or?
Yeah, I think we still have some like continues gradually come. Yeah, maybe we wait 1 more minute, I think.
Sure, sounds good.
Mhm.
Can we start now, maybe?
Yeah, yeah.
Ready? Oh, cool. Thank you. Thank you everyone for joining us for this webinar of Inform's Quality, Statistic, and Reliability cluster. And today we are really honored to have our speaker, Dr. Xiao Liu from Georgia Tech. I will just start with a very brief introduction about our speaker today, and then we will start the webinar. So during the webinar, we would request all the audience to mute your microphone, and then whenever after the webinar, you can ask questions for the Q&A part. You can ask questions either by unmute yourself or type your question into the chat box. Either would work. So Dr. Xiao Liu is the David McKenney Family Associate Professor at the H. Milton Stewart School of Industry and Systems Engineering, Georgia Institute of Technology. His research focuses on domain-aware, data-driven methodologies for various scientific and engineering applications, and research findings have been published on both industry engineering and statistical journals. For example, NASA, Technometrics, IIC Transactions, so on and so forth. He served as the president of the Data Analytics and Information System Division of IISE and will serve as the program co-chair of the 2025 IISE Annual Conference and Exposition. Before joining Georgia Tech, he held positions at National University of Singapore, IBM Thomas Watson Research Center, and also University of Arkansas. So without further ado, let's welcome Dr. Liu to start his webinar.
Thank you. Thank you, Dr. Tian. I just want to take this opportunity to thank QSR and Dr. Wenmeng Tian and Dr. Chao Wan for giving me this opportunity. And it's such a great pleasure for me to spend like 1 hour in this early afternoon and share with you my recent work. And also, I see some old friends in the participants list. I just want to say hi to everybody here. Okay, so let's go. And so the topic of my today's presentation is about statistical learning for scientific and engineering processes. And I will talk about a few papers. So in this field, and some of them were completed by myself and some of them were my students' work. Okay. So now, if you think about many nonlinear dynamical systems in scientific and engineering applications, so perhaps this is the most important and representative form of governing equations behind many scientific and engineering applications. So here, what you can see is the S is the state that can change over space and time. So X is the space, right? And that's what we're interested in. S is usually a long vector if we discretize it. And the second term, G here, is a nonlinear function, right? And that takes the X as the input, and we also have F. F is the external forcing term. So we can find lots of examples, right? So for example, advection diffusion equations, heat transfer, Navier-Stokes. So all these processes more or less can be written into this form, right? So I can give you more examples. For example, if you look at this environmental processes, for example, the first one is the hi, one more, can I ask a question? So
Sure.
the slide that I'm showing right now, which is, are you looking at the animations right now, or you're still looking at the equation?
Equation.
Equations, right? Okay, so now you can see the animations, all right?
Yes, correct.
Okay, great. So I just want to show you some numerical, some examples of different type of processes. For example, if you think about the pollution, air pollution processes, if you think about the extreme weather, rainfall precipitation processes, or the wildfire smoke dispersion processes. So all these are natural processes governed by the laws of nature. If we look at the governing equation behind these processes, so many of these processes are spatial temporal, physical advection diffusion type of processes whose dynamics can be governed by a PDE that you're looking at here, showing on the screen. I'll come back to this PDE later, but my point here is that this PDE, advection diffusion equation, can be written in the previous general form, as you can see here in this slides, right? It's just like one example of the general expression. And also, this is another work done by my student. If you look at the structural dynamics between the aircraft and UAV collision. So this process can be described again by a partial differential equation shown on these slides, right? And so I come back to this example again, and my point is that we can sort of rewrite this PDE in the previous general form. So here the question is, if we're dealing with data arising from this type of PDE, so if there's a good way for us to model data arising from this PDE, right? So if we can answer this question, we can apply this methodology or this modeling approach to solve many engineering and scientific problems, right? So that's the goal of this presentation. I'm going to share with you some of the work that we've done that enable us to model data arising from this general form. Okay, so let's come back to the advection diffusion equation. I just want to provide you with more background and my motivation here. So if you look at this advection diffusion equation, so you can see here is the spatial temporal process of interest. And A here is the advection diffusion operator. So it depends on some physical parameters. For example, V is the velocity. So we may or may not know it, right? So D is the diffusion, and here we have the decay, right? So to solve a problem like this, we can absolutely use physics-based approach. For example, we can use numerical approaches to solve these PDEs, right? So there are certain advantages for doing this. We can use these physical models to do control, design, and planning, and what-if analysis, even before we have any data, right? For example, right now I'm trying to run this fire modeling, which is a physics model, which is called the WR fire model. So this is basically a physics model that involves a set of partial differential equations. We just use numerical methods to solve those PDEs. And of course, there are certain challenges, right, associated with those physics models. This is definitely not a criticism, right? So we're faced with some challenges. The first one is real-time prediction due to the computational complexity of many of these physical models. And for the same reason, it can be hard for us to incorporate, streaming data in real time because it takes time for us to run the physics model. But we have, streaming data coming in, like, for example, every second. We certainly cannot just, input those streaming data into the physics model, which is already running. And sometimes we notice that these physics models may not perform very well for short-term prediction because we need to specify lots of, the values for many parameters for the physics before we can run this physics model. And those parameters are usually unknown. Okay, so for this reason, people have also tried to use, spatial statistical models to model spatial temporal data arising from these physical processes. The central idea is to generate to build some random processes with some specified joint space-time covariance structure. And there are certain advantages of using statistical approaches. For example, we can incorporate observations, we can scientifically capture and quantify uncertainty, and usually these models perform reasonably well for short-term predictions in a real time. And of course, using those statistical models are sometimes we're faced with some other challenges. For example, the model specification. So if you think about it, if I want to build a random process, I need to specify the space-time covariance structure, right? Following the traditional approach. But for a real physical, complicated natural process, for example, it's going to be very hard for us to specify the parametric structure of the space-time covariance function, right? Because that function can change over time, meaning that it might not be stationary, it's space-time inseparable, and so on, right? So if we're not able to specify a good covariance model, so we're going to have some issue interpreting the model and use the model to generate some actionable insights. I think that's what the end users they care about. So based on this, observations, I believe there are both theoretical significance and practical needs for us to explore the convergence between physics-based modeling approaches and statistical modeling approaches, such that we can enjoy the benefits provided by both approaches, right? For example, we can come up with models that incorporate physics so that a model is interpretable. We can incorporate observations, especially streaming data, and we can make the model computationally more efficient for real-time operations. So this is like the motivation behind my entire research over the past couple of years, and I believe I will keep working along this direction for a few more years. Okay, so let's come back to the previous question. Since we're going to do this, so the question is, how can we model data arising from this type of PDE? Okay, so before we can answer this question, let's take one step back to see what is the existing computational scheme for solving a PDE like this. So there are many methods out there, of course, but there's one important method which is called the separation of variables, which depends on eigenfunction expansion. The central idea is that here S, right? So that's the quantity of interest. We express this S as the multiplication of two components, a temporal component A and a spatial component psi. So the temporal component is used to capture, the temporal patterns, time dependence associated with this process. And the spatial, the second function, the spatial function captures the spatial dependence, which is essentially the eigenfunction. So these functions are orthogonal, to each other. Okay, so why this method is important? Because these eigenfunctions are orthogonal to each other. What we can do here is that we can multiply this eigenfunction to both sides and then take the integration over space. So this is known as the Gaussian projection method, which is a very famous and well-known, method in solving PDE. So the consequence of doing this is that we can obtain the temporal dynamics, the ordinary differential equation that governs the temporal dynamics of A here. So once the eigenfunction psi is fixed, in other words, so this approach enables us to convert a PDE that is defined on both space and time to a set of ODEs, which captures the temporal, dynamics of A. So this, later on, you will see that this will bring us lots of modeling, advantages when we try to model data arising from this PDE. For example, if you think about, how we can solve a 1D heat equation, this is a very simple PDE. In this case, the eigenfunction can be, we can use the Fourier function, the Fourier basis as the function basis, right? We perform the Fourier transform, we are able to convert this PDE, which is defined on both time and space, to a set of, ODEs here. And the nice thing for this simple example is that we actually have a closed form solution for this ODE. So we're able to solve this, heat transfer equation analytically, right? So this is the key idea, right? So once the eigenfunctions can be found, and then we can convert this PDE to ODE, and then we can just focus on the modeling of this ODE using statistical approaches. For example, as you can imagine, we can model the dynamics of this A by a temporal, stochastic process. So you'll see that's what we'll do later. Okay, so motivated by this existing idea, so let's come back to this advection diffusion equation. We're going to follow the same idea. So we're going to, express this this space-time process C as the multiplication of two components. The first component, phi, is a function of space only, right? This is basically a set of basis functions that span a spectral space. So we can find these basis functions using different approaches. For example, we can use proper orthogonal decomposition, POD, which is a data-driven approach, or we can use Fourier basis. In other words, we can just specify, the structure of the basis. So later on, you're going to see, I'm going to talk about both approaches. So once this basis functions, has been completely fixed, then the second component, alpha t, right, can be captured by a stochastic process described by a stochastic differential equation, right? So now we add the stochastic term to it. So the ODE becomes an SDE, stochastic differential equation. So this SDE basically describes the temporal dynamics of this alpha, which is a long vector, of course. Okay, so I can show some examples here. For example, if you're dealing with a weather radar, images taken from a precipitation process, right? So we can use Fourier basis as the eigenfunctions in this case, for example, and then we can actually visualize the dynamics of alpha over time, as you can see here in this animation. So alpha is a complex number, so we can see this is the dynamics of both the real part and the imaginary part. Right, we can zoom in a little bit here. So alpha is a long vector, right? So if we just look at the top three elements of alpha, we could actually plot their trajectories. We can see, how the top three elements of this long vector alpha, evolve and progress over time. So because these basis functions are fixed, then in a subsequent modeling, steps, we just need to focus on this stochastic differential equation that captures the trajectory, the dynamics of alpha, right? So that's the basic idea following from this separation of variables approach, which has been known for decades when people used to use this method to solve PDE. So the key here is to determine the structure of this stochastic differential equation if there is a parametric structure there, right? So now we have two approaches. The first approach is to use pure data-driven approaches to basically learn the dynamics of alpha. This is possible, right? Because, for example, we can assume that this alpha follows this polynomial structure. This is a second order, equation. Then we can just need to use data to estimate this G matrix, this H matrix, for example. And there's some other approaches which are available out there. But in this work, we want to take a different approach. Basically, we go back to the original advection diffusion equation, as I showed you previously, because sometimes from this advection diffusion PDE, we're able to obtain the structure of this SDE. In other words, we're able to determine the structure of this G in this case, right? This is obviously not always possible, but once it is possible, we can sort of, inject or, embed physics into the statistical model, because then we can make a claim that G takes certain structure, not because we made the assumptions, it's because we're dealing with data from this PDE, then G must have certain structures, right? So if that's possible, then we can justify, our modeling approach. We can connect our statistical model to the PDE and to the physics. For example, we can do this using the Gaussian projection method. That's one of many approaches that we can take. Okay, and then if you think about it, if this is possible, then we can sort of convert the entire modeling process, the modeling of a spatial temporal process, to the modeling of a multivariate stochastic process, alpha. This is essentially the conversion between from PDE to ODE, right? So we build a statistical model on top of ODE, not on the original PDE. And then the dynamics of alpha can be determined by the governing equation, by the physics. We have talked about that. If this is possible, this provides a very natural way for us to embed governing physics into the statistical model. And then once we have a statistical model for alpha, so we know the temporal, covariance structure for alpha, and then because the original process and alpha has this linear relationship, we are able to obtain the space-time covariance structure for the original space-time process. And since the dynamics of alpha is determined by physics, and then we hope that the space-time covariance structure for the original process C also has some reasonable physical interpretations, right? And the last benefit that we can expect from this approach is that we can always do dimensional reduction by keeping, the number of only the low frequency terms in alpha. We can just drop those high frequency terms in alpha. Okay, so these are some potential, modeling benefits that we can expect if we adopt this approach. But in general, if we're going to use this approach, we can envision that our statistical model will take this form, right? It's a dynamic model, it's a state space model. The first line is basically the eigenfunction decomposition. So if we use Fourier basis, so the first line is basically the Fourier transform, right? But it doesn't have to be. And the second line captures the dynamics of alpha. That's basically a set of ODE there, right? And this G is determined by the PDE, by the original governing equation, right? So this is the end goal, right? Following this idea, we can envision that this is the kind of model that we can build. Then the question is how to get there, right? So in order to, build this model, we need to answer some fundamental questions. For example, what's the parametric structure of G? So this is the key, right? If we cannot answer this question, then the entire exercise becomes meaningless. So that's the first question. And the second question is, once we know the structure of G, so once we know have a statistical model for alpha, so what is a physically meaningful space-time covariance structure for the original process C? Because we're building a statistical model here. So we need to be able to obtain this sampling distribution for C. And the next question is, for example, how can we, embed this results into a state space or dynamical statistical model? And of course, for real-time operation, we need to make sure that we have a computationally efficient method to perform statistical inference. So of course, I don't think I'm going to have time. I have time in today's presentation to go into all these details. But if you're interested, so I provide some papers, right? So the answers to these questions are provided by these papers, okay? And so if I go to the next slide, I just want to pick, one important results here and show the results to you. Because the first question is, what's the dynamics of alpha? In other words, what's the parametric structure of G? It turns out for a Vection diffusion type of, equations, we're able to obtain the parametric structure of the stochastic differential equation that governs the temporal dynamics of alpha, which is shown in this equation 3. So this is the proposition 1 in this paper, right? So G here is a matrix. If you look at individual element of the G matrix, so this is the closed form. We have a closed form expression for the individual element in the G matrix. And if you take a closer look, you realize that this G matrix actually depends on the physical parameters, right? So for example, the diffusion, the decay, and the velocity field associated with the advection diffusion operator. So therefore, this G, the elements of this G, this structure is determined by the PDE, right? So then once we have data, we just need to estimate this velocity field, to estimate this diffusion, estimate this decay, while maintaining the structure, which is motivated by physics. So this is what I meant by we can, embed physics into statistical model to enhance the interpretability of our statistical model. Right, so this is like one of the main results reported in that paper, but we have many other results in that paper. If you're interested, you can take a look at the paper. Okay, and of course, we apply this to some applications. So what you're looking at right now here is that we apply this method to predict, precipitation using weather radar images, right? So the first line shows the performance of our approach in terms of the mean squared error, right? And the second line and the third line are two competing approaches. So what you can see is that at least in this particular example, we can see the advantages of the proposed methods. And the takeaway message here is that both accuracy and interpretability can be simultaneously improved by integrating governance physics into data-driven models. I personally think, because I'm from the School of Engineering, I think this is important because we're dealing with physical and engineering processes governed by the laws of nature or engineering, right? So at least there's a hope that we can improve both accuracy and interpretability at the same time. So this is about the fundamental modeling framework. So after we have constructed this framework. Okay, I'm sorry. I have a question. You mean Gaussian process models? Should I answer this question now, or maybe I can answer it later? Yes. Yeah, but anyway, but I think the comment I can make here is that our proposed model is also a Gaussian process model, but the covariance structure is obtained from the PDE, right? So we're going to have a Gaussian process model with space-time inseparable covariance structure, and it's isotropic, meaning that it can change. It's different along different directions, and also it's non-stationary because it depends on the physical parameters that change over time. But I don't have a slide showing that in today's presentation. But yes, the answer is our model is a Gaussian process model with a special space-time covariance structure. Yes. Okay, so then on top of this framework, we did some extensions. For example, we look at how we can fuse data from multiple sources and how we can use this model to solve inverse problems, and then it leads to a sensor deployment problem, which is what we're currently working on. So I can briefly talk about these extensions. The first one is about the integration, the fusion of data from different sources. Okay, here. So the motivating example is like this, right? So the wildfire is a big issue for solar energy production because the fire generates smoke and the smoke blocks the sky. So in that case, the solar panels on ground are not able to produce sufficient energy. So as you can see here, so the solar generation actually drops, right? So once the PM 2.5 goes up, this is because there was a fire at that moment, at that time. So the question here is are we able to, model the dynamics of the smoke propagation, right? So that's important. If we know where the smoke is moving to, and then we may be able to take actions in advance. And so what we have here is that we have almost the real time. So every 5 minutes, so we have this satellite image data coming from 2 satellites. One is called GO-16 and the other one is GO-17. So these are 2 geostationary satellites, meaning that they're hovering above the sky and they're looking at the area of interest all the time, right? And so, but the challenge here is that the data that we got from different satellites are not the same, right? They're supposed to be the same if everything were perfect, but that's not the case. So what you're looking at here, are the data coming from 2 satellites, are looking at the same area over the same period of time. You can clearly see that the observations do not agree with each other, right? So first of all, the quality of the data are quite different. So from the satellite on the left side, we see lots of missing data. And sometimes even the readings are different, right? So for example, if you look at the area circled by this green circle, obviously the satellite on the right side can see the fire, but the satellite on the left side cannot see the fire. So there's a natural question here we can ask here is that how can we fuse data together to make sure that the fused data also makes sense from the physics perspective, right? So obviously we cannot take the simple average between this of these 2 observations. Okay, so it turns out our modeling approach can easily handle this approach because we can still build this dynamical model. The second line, the dynamics of alpha remains the same because the dynamics of alpha is determined by the physics only. It's not determined by the observation, right? So that means that the bottom line here, the third equation is exactly the same. We don't have to make any changes there. But now we have 2 sources of observations, but we can still put them together, right? So to form the observation equation in a state-space representation. So if we do that, naturally, you can think that we are able to extend this model such that this model can handle multi-source, heterogeneous source, streaming data. And because this entire, model is driven by the physics layer, which is the dynamics of alpha, So the fused data also makes sense from the physical perspective, of course, in a relative sense, right? Okay, so this result is presented in one of our recent papers. If you're interested, you can always take a look at the paper. And also, so far we have talked about a forward model, right? So we can also use this approach to solve inverse problems. So what is an inverse problem? So basically, we want to estimate the parameters associated with the model such that the output of the forward model is as close as possible to the observation, right? For example, here, theta can be the emission rates from different emission sources, and F is the forward model. We can use our previous, the model as the forward model. And then, of course, given this theta, this forward model generates some predictions. And then once we have observation, we can do a cross-check, right? To see if the forward model is accurate enough in terms of explaining the observations. Then we want to estimate theta by minimizing the discrepancy between forward model output and observations. All right, so this is in general, in a nutshell, what inverse model do. And so in our work, we consider, M number of monitoring locations. So we have M number of sensors deployed, and we monitor the process for L time periods. And our goal here, at least in this paper, is to estimate the initial condition, basically the spatial temporal process at time 0 over the entire spatial domain. Because we don't have observations over the entire spatial domain in this case. We only have discrete observations from these sensors, but we want to estimate the entire spatial, process at time 0. Okay, so that's the goal here. And we sort of extended our previous model to achieve this goal. So now we have this forward model. So what you're looking at here, this is a simplified version of the previous model that I showed you. So in this model, we assume that all those physical parameters do not change over time, right? In our previous model, the wind, the velocity, the diffusion, the decay, they can all change over time. But here we'll make the simplification such that none of these physical parameters can change over time. So if that's the assumption, we can end up with a linear model, a linear forward model like this. Based on this linear forward model, we can come up with an inverse model, which is essentially a least square, minimization problem with the sparsity regularization and the smoothness, regularization. So we can solve this using ADMM. So in our paper. And also we consider different sampling schemes. So we consider, irregular grade in a sense that we can, arbitrarily deploy sensor anywhere we want to. And we also consider a shifted uniform in the sense that we have two uniform sensing platforms, but we shift one of them from the other one a little bit. So we have two shifted uniform. We can have multiple sensing platform like this too. And we also consider non-uniform sampling. It's like we have a uniform, sensing platform, but we remove some of the columns and rows. So we have a non-uniform sensing platform. So we have some special algorithms particularly designed for each of this sensing sampling scheme, which are reported in this paper. But this paper is actually based on our previous model, the forward model that we previously built. Okay, this is about the inverse problem. And so obviously the quality of the inverse model depends on where we collect data, right? So this naturally leads to one of our current ongoing work. So one of my students is working on this, which is the sensor deployment, because this determines, where data comes from, and that will then determine the quality of the inverse model. Since we're working on this, I don't think I'm going to the details for this problem, but I can briefly share with you what we're currently working on. We assume that we know the locations of the emission sources. You can imagine we know the locations of the factory chimneys, the stack, right? And each source is either leaking or not leaking. So we have two states for each source. And we consider a steady concentration field to make everything easier to be handled. And there's a critical assumption here is that the number of sensors is less than, and usually much less than, the number of sources. So this actually gives rise to the optimization problem. Otherwise, we can just deploy at least one sensor to one source and we're done, right? Because we know the locations of the sources. So we have less number of sensors than the number of sources. So the optimization problem that we have looks like this, right? The outer level, so we try to minimize the average estimation error. right? So this theta hat, that's the output from the inverse model. And for the inner level, that's we want to solve the inverse problem. So of course we have two nested problems. That's why we have a bi-level optimization problem. So at least that's the current formulation. Of course, there's some details here that I don't have time to mention those details. Yeah, we can solve it using sample average approximation, and we can show some performance guarantee there. And I can show you one example here. For example, you can see that if we have 50 sources and we can deploy 30 sensors, so the figure on the right side basically shows you the trajectory of those sensors moving from their initial location to the final location as we run the algorithm, right? So we run this optimization, we try to solve the optimism problem. It takes multiple iterations. After each iteration, we move the sensor location a little bit. So what you can see here is basically the trajectory of the sensors moving from their initial location to their final location. So we can actually get some insights here. For example, because in this simulation, the wind comes from the north, that you can see that this algorithm always deploys some sensors at the south boundary, right? Because the wind comes from the north direction, and no sensors are deployed along the north boundary. So this makes perfect sense because we want some sensors to guard the southern boundary, because the wind comes from the north. We want these sensors to pick up the signal from all these sources. Of course, this is something that we're still working on. So next month, I believe one of my students will present this work at the ISE conference in Canada. So if you happen to be there, so you're most welcome to join our session. So we'll be happy to present you with more details here. Okay, so this is like some of the applications in the area related to environment and energy, and then I'm gonna show you some other applications. So in this application, we're looking at the collision, the modeling of the collision process between aircrafts and drones, right? So people need the inputs for them to make regulations and make changes to their existing, policy. So if you look at this process, it's basically governed by this partial differential equation. So rho is mass, right? So u is displacement. So the second order derivative of u, that's acceleration. And the second term, that's the internal force, and the term on the right side, that's the external force. So this is basically F equals ma, right? The second law of motion. And of course, we can numerically solve this equation using finite element analysis. So my students did this work. And it took us about 20 hours plus to simulate one collision process under one impact condition. So of course, if we have like hundreds, thousands of impact conditions, there's no way for us to run this over and over again, because each run takes about 20 hours a day, right? So what we did was we used the same modeling approach, right? So we start with this full order structural dynamics, the physics model, and then we perform this eigenfunction decomposition. But in this case, we use proper orthogonal decomposition, so that this V is called the POD basis. It's called the POD basis, right? And which can be learned from data by solving this optimization problem. We actually have closed form solution for V. This is well known. And so once this basis have been fixed, and then we can focus on the modeling of the dynamics of Q. So in this case, the Q is the reduced order states of the system. And then we use the same Galerkin method, but with a different basis, we can obtain the reduced order model. So this is, again, well known in the literature. There's nothing new here, right? So we just borrowed the existing framework. So again, what you can see here is that we convert this, we have this ODE, right? So which captures the dynamics of Q. Okay. So just one example, you can see this is how the POD basis look like. I show you the top 10 POD modes, right? And so the proposed statistical learning and prediction framework looks like this. In this time, we need to generate data by solving FEA, the computer models. In the previous example, we have sensor observations, satellite observations, but for this example, we don't have observations, right? So we have to solve this numerical models to get some data. So from where we can, start building our model. And then combined with the full order governing physics, we can obtain this reduced order model. This is what I showed you in the previous slides. And then a statistical model will be built on top of the low dimensional reduced order model. And the statistical model has two components in it. So the first component captures the relationship between parameter and external force. In this case, for example, if we know the impact conditions, such as the angle, the attitude of the drone, so this component can tell us the external impact force applied to the aircraft surface, which is also a space-time, process, right? And the second component links the external force to system states, which is the aircraft surface deformation in this case. So once we have this model, given any new parameters, we're able to use this model to quickly predict the aircraft surface deformation, right? So we published this paper last year. So there are more details in that paper. But I can show you on a very high level how this works, right? At a new collision condition, parameter P star. So we have a multivariate Gaussian process regression model that gives us the coefficient that determines the external impact force. Then we have a function-to-function, profile regression that enables us to predict the reduced order state from the external force, and then through the inverse process of the proper orthogonal decomposition, we can recover the full order system states. In this case, the aircraft surface deformation. Right? Let me show you some output here. For example, we consider 3 parameters. These are the angles before the collision happens, right? The pitch, yaw, and roll degree of the aircraft, of the drone. And we use a space filling design. So basically solve this numerical, this PDE at these 35 impact conditions. Once we have determined, the experimental conditions, so we can run FEA to generate some data. So as you can see here, so this is like one illustration of how the simulated or FEA generated, aircraft surface deformation process. You can see the collision center, the propagation of stress, and some new deformation area being formed at the edge of the spatial domain. Right, and this one shows you the output of our model for that particular location. Right, so the animation, the bigger one, is the one generated by the statistical model, and the smaller one on the top right corner, that's the output from the high fidelity FEA. So they're not exactly the same. They will never be exactly the same, but you can see that it looks like the statistical model can sort of capture the dominant, spatial patterns associated with this spatial temporal dynamics, right? So that's what we want to achieve here. And so this is just another view of this, right? So the first row shows you the predicted, aircraft surface deformation at the final moment along the X, Y, and Z directions. It's a 3D problem. And the second line shows you the actual. The actual means that that's simulated from FEA. And the last row, the bottom row, shows you the standard deviation, because now we're building a statistical model. We are able to, quantify the uncertainty associated with the output, but it's going to be hard for us to do that if we just run FEA, right? So that's another advantage of using a statistical model. This will naturally lead to sequential experiments and experimental design problems once we're able to quantify the uncertainty. So this slide just provides you another a closer view of this. We look at the predicted deformation at 3 locations. So the red line shows you the aircraft surface deformation over time at that particular location, and the blue lines are from the FEA simulation. You can see the agreements between the red one and the blue ones, right? Again, they're not exactly the same, but that's not what we want to do, right? We just want to come up with a computationally much faster, and physically meaningful surrogate model so that people can make quick decisions. In general, so at least in this example, we have this leave one out cross-validation error. The mean error is about 13%. For some cases, the error is higher, up to 18%, but for some cases, the error is really low, about 10%. Right? But in terms of the computational time, so our statistical model is actually like 1,200, more than 1,000 times faster than the numerical simulation using FEA. And the price that we pay is this 13% on average prediction error. So the trade-off is clear, right? So we can make this entire process much faster as long as we're willing to pay this 13% average prediction error, right? It's not a prediction error, it's the discrepancy between the statistic output, between the output from the statistical model and the output generated by FEA, assuming that FEA gives us the ground truth, but that's debatable, right? That may or may not be the case. Okay, so this is what we have there, but another issue that we're currently working on is if we come back to this separation of variables, this framework, this spatial function, this eigenfunctions psi is once it's found, it's fixed, right? So in the first example, we use Fourier basis. In the second example, we use POD basis. But they're all fixed once they're found from either from data or pre-specified. But this may or may not be true. Reality is because if we think about the second example, the aircraft collision problem, right? So given the collision scenario, which is the parameter, we can generate some data using FEA, and then based on the data, we can learn this POD basis, right? And then we build a reducible order model based on that POD basis. So as you can see that this POD basis depends on the parameter, which is used to generate the data. So if we repeat this process, we have a second parameter setting, so we're going to have a second basis, and on, right? So if we have n scenarios, if you run this FEA n times using n different parameter settings, so we're going to have n different POD bases. And the question here is that what if this POD bases are very sensitive to parameter changes, right? So the point is, if we change the parameter, but the POD bases are pretty much the same, then we're good. But in reality, that's not the case. For example, if you look at this aircraft collision problem, so each row shows you the top 5 POD modes for different collision parameters, right? Collision conditions. You can see that the POD modes actually change as we change the parameter. This basically suggests that there is a need to build a model between the parameters and the POD basis, such that in the prediction step, if I have a new parameter, so I can use this model to predict the new POD basis or to update, to adjust the new POD basis based on which my new reduced order model and my new statistical model can be built. So this is like a missing component in our previous work, right? So what we need here is that we really need a statistical model that establishes the mapping between parameters and POD basis, right? Which span a subspace to which the high full order systems can be projected to. This is something that we've been actively, working on. So we start with something simple. So we try regression trees because we believe that's simple enough on Grassmann manifold for adaptive and reduced order models. This is like our preliminary work, a proof of concept. We just want to test if we can use some statistical, regression methods to capture the relationship between parameters and POD basis. If it turns out to be possible, then we can later on build more advanced models for the same purposes. So this is like a one illustration for the aircraft collision problem, how the tree looks like, right? So we look at the yaw degree first, and we put some samples into the left daughter nodes. And for these samples, we're going to use one POD basis. And for those samples, we're going to use the second POD basis, the third POD basis, and the fourth POD basis. In the sense that if you give me some new yaw pitch and roll degree, this 3 degrees, right? So based on this tree structure, we can determine, what's the optimal POD basis that can be used for that particular parameter. Right, and we published this paper on an aerospace engineering journal because we believe many audiences there may be interested in this kind of work. But I have to say that regression tree is not known for its accuracy, right? So it's very bumpy, the outputs, right? It's either POD basis 1 or POD basis 2 or 3 or 4. But this paper actually serves as a good proof of concept that shows this approach might work. Then following this early preliminary results, right now what we're doing is that we're using Gaussian process for the same purposes, right? For the same purposes. The idea is that, so let me go to the next slide here. The idea here is that each POD basis span a subspace in a Grassmann manifold. So each subspace is represented by P in this figure. So you have P1, P2, P3, 3 subspaces spanned by 3 POD bases. And our goal is to build a Gaussian process on the Grassmann manifold, but we cannot do that directly. So we cannot directly build this Gaussian process on this Grassmann manifold. But what we can do is that we can build this Gaussian process on a Euclidean space with a different dimension. And then we can establish the connection between this Euclidean space and this Grassmann manifold. That's the gist of this paper, right, in a nutshell. And so if this is possible, then what we can do is that we can always build the Gaussian process, make the predictions in Euclidean space, and then we can map the results back to the Grassmann manifold, which tells us, the optimal POD basis for a new parameter. Okay, this work is almost done. So if you're interested, I'll be happy to share with you our paper. So it will be on our archive very, very soon. So I'll put it there. Right, so I can show you one example of how this Gaussian process model for adapting POD basis work. So we're looking at this very classic, flow over a cylinder example. You can see the flow comes from the left side and there's a cylinder there. And over time, you can see the so-called von Karman vortex, right? The wake effect. And this is the equation, the physical equation behind this. So we're using this BGK approximation to the Navier-Stokes equations. So we use the code, which are publicly available from the internet, from GitHub. And there's one parameter here, which is the time scale tau, that is related to the kinematic viscosity. So we basically try to see if we can build a model such that if we change this value of tau, if that model can tell us the optimal POD basis for that new parameter, right? And after that, we compare our performance to existing approaches to see if we can have an improvement, right? This figure is just to show you why we need to do this. The one on top, this is when tau is 0.53. These are the top, this is not a top four. These are the POD modes 1, 4, 7, 8, 10 for that parameter value. If we change the parameter value, you can see the POD modes 1, 4, 7, 10, they look completely different. That simply means if I change the parameter, I also need to change the basis, right? I also need to change the basis. If you think about the subrouting of variables approach when we solve PDE, right, we have eigenfunctions. The bases are the eigenfunctions. That means we need to adapt the eigenfunctions when we change these parameters. So we implement the current version of our models, and then we do the comparison. So what you can see here is that you can see 3 lines here, right? The horizontal axis, that's the different testing cases. The vertical axis, that's the L2 error. So the Frobenius norm for matrix. The blue dashed line, that's the output of that's the performance of the existing interpolation of POD method, which is based on the Lagrangian interpolation. So that method has been there for 10, maybe 20 years, which are widely used by the engineering community. And the red solid line shows the performance of our current version of our current method. So you can see the improvements, right? Especially on the 2 ends of this design space. Right, in the middle part, so I think all 3 methods, they have pretty much the same results, but on the 2 extreme ends, so you can see the red line actually, which is our model, so provides the best the model performance. We can see the improvement there. Right, so right now we're testing these approaches using different some other approaches, and then we're also trying to complete the theoretical some investigations associated with this research. Okay, so I will use 1 minute to conclude this presentation, so we have some time for questions. So in this work, I basically shared in this presentation, I basically shared with you some of our recent research about how we model data arising from this general form of PDE, right? A direction diffusion equation, the structural dynamics. But more or less, these PDEs can be written in this form. So that the idea is that if we can come up with something that can solve a set of problems, right? So the impact will be quite big, right? Because we can apply the same method to many other engineering problems. For example, if you look at the heat transfer process, I think my student is working on this one. This PDE essentially can be rewritten more or less into this form. That means we can apply the method here. We look at the Duffin equation, the nonlinear dynamics of wind turbine. You can see the vibration. So we can also basically write this equation into this general form. That means there's a hope that our method can be applied to solve many applications. Okay, this is the final slide. So in general, I believe this is a very interesting research area, and there are lots of things that can be done. So everything that I have presented, I see them as my preliminary work, because the more we work on it, so the more issues that we could see But at least I think those previous work demonstrate the great potential and the broad impact of leveraging domain-aware statistical learning for a potentially wide class of applications, as you have already seen, right? That traditionally rely on computationally expensive numerical models. I think this is important for people from engineering. I'm from engineering school, as I mentioned, so we're dealing with engineering and process scientific or natural processes. I think it is important for us to explore investigative methods that enable us to integrate some domain knowledge and also data-driven approaches. Okay, so I think that's all I plan to present. So before I can conclude, I would like to thank QSR, Dr. Wenmeng Tian and Dr. Xiao Wan again for giving me this opportunity, and also, of course, NSF for supporting my research. And of course, two of my students, they've been working with me for a couple of years, so they did most of the work so that I can present their work today. And of course, I appreciate that you spent 1 hour of your time with me. I hope I didn't waste your time. So thank you. I appreciate that. I can take some questions, I guess.
Thank you. Actually, there are already questions in the chat box.
Yeah, let me start from the first one. The first question is from Ron. Did you use experimental design on FEA to model parameter settings impact on PUD basis? Yes, we use space fill in design. We use space fill. So if you think about if we have the statistical surrogate model, so we can certainly do sequential experiments. That means we can use the statistical model to guide us if we have additional computational budget to run more FEA, where at what parameter settings we should run this FEA, right? That's a natural question. We haven't started working on that, but that's our plan. Any thoughts on how to provide improved diagnostic using have you looked at Bayesian optimality? I think these two questions are related to experimental design, so we're not there yet, especially the third question, Bayesian optimality method. Yes, I don't have a specific answer for that question because we haven't done that, but I think it looks like something we will look into when we move on to the experimental design stage. Yeah, thank you. The second question from Xiao Liu. Thanks for inspiring. I have a question for S. Is it possible to consider as a density to model the gradient flow of framing manifold? Considering the geometry of the interesting process model, is it possible directly model push-forward probability measured to reflecting the shape of? Okay, I think this question, is it related to, because you mentioned grasping manifold, I think this question is related to the adapting of PUD modes, that work?
Yes.
Yeah,
So
I think that's a different.
say that out.
So I wish I had more time to explain that, but I think it's a different issue here. The issue here is that for different parameters, we need to find a basis, right? And each base spans a subspace, and the collection of the subspace forms this grasping manifold. So in this simple example, we have 3 parameters, so P1, P2, P3, so we have 3 subspaces. They're all in the grasping manifold. So the question here is that if I have a new parameter, I need to predict this P star, which is the new subspace in the grasping manifold. So you mentioned the propagation issue. I do not think it's the issue that we're facing in this problem, right?
Thank you.
Yeah, but I think you must have done something in your mind. So I will reach out to you after this to see to get a better understanding of your questions.
All right, thank you, Dr. Liu, for your presentation and for your answering all the questions. Are there any other questions, as we have 1 more minute left? All right, if no, then if you have further questions, please feel free to reach out. And actually, there's one more as I'm speaking.
Oh, thank you.
That's a thank you note. Yeah, anyway, thank you so much. And if you have further questions, please feel free to reach out to Dr. Liu for further discussion. And thank you so much for everyone joining us this afternoon. And hope you guys have enjoy the rest of your day.
Yep,
Thank you
very
Dr.
much. Yep. Take care.
Bye-bye.
Thank you, Dr.
谢谢。
拜拜。